Now let's talk about the place on the OSI model where network engineers begin to care. That's the transport layer. You can see this is one of the few layers that is exactly the same between the TCP/IP and OSI model. So in the previous video, we talked about how these three layers are self-contained within the application that wants to communicate across the network. And as network engineers, we usually don't get involved in that too much unless we're dragged into it by the application folks. This goes back to the War of the Worlds. Essentially, the network and application people that battle back and forth between something not working. The application people go, must be the network. Our application seems to work just fine in blah, blah, blah environment. And we go, hey, I can ping it. Well, when that argument doesn't fly, we get dragged into troubleshooting applications and sometimes expose that, it really was the network. Or, oh yeah, your application seems to be doing something right there. I don't know what it is, but it's not working across the network environment. So push that aside. We now have the application that has said, I'm going to communicate across the network. It's identified to its operating system, got some data for you right here. Now what happens? Well, at the transport layer, the operating system makes a choice. Now, the choice is dictated by the application. So I don't want you to think that URI or Windows or Mac OS or whatever operating system we're using actually makes this choice for the application. It's decided when the people who create the application do it. It's a choice of protocol. Now, many of you know that TCP/IP is not just one protocol. The name itself should give it away. TCP and IP are two completely different protocols that are combined together to create some functionality. But this is kind of like Microsoft Office. Nobody says, oh, I'm going to use Office to type a document. They might say, I'm using Word to type a document, or Excel to create a spreadsheet, but they're all part of the big package called Office. Well, inside of here is a whole suite of protocols. TCP and IP are the obvious one because it's in the names, but there's UDP, there's ICMP, there's all kinds of different protocols that go into this big package we call TCP/IP. And at the transport layer, we have our first decision on what protocol are we going to use. Usually, it boils down to a choice between two, UDP and TCP. In a nutshell, UDP, which stands for the User Datagram Protocol, is unreliable but really fast. This is useful when we're dealing with real-time communication. Think about it. What kind of communication on a network uses real-time? Video streaming, right? You're streaming a movie and watching this movie as it's happening, watching a baseball game. I mean, live TV is streamed across the internet. That's not a new thing. Audio conferences, voice over IP. You're having a phone call over the internet. That's what I mean by real time. You're playing an online game, right? You're moving your character. He's running on the screen as you're pressing characters. That's real time. And the reason that I say real-time relies on that unreliable protocol is because if you lose some data from that communication, you're not going to really care to resend it. For example, let's say we're having a phone call, and just for the discussion, let's say that every packet that goes across the network is really a word. This one says, hi, how are you? We don't care what comes after that. Right? So let's say that all the word all, well, I'm Xing it, but I can't say it. The word how gets dropped, right? So at the other end, the person hears, hi, are you? Now they're going to be able to piece that together and go, oh, okay, I heard kind of a glip in the conversation. He must have meant how. Okay, so the point is there's no use in sending that packet again at a later time. The conversation has moved on. Hi, are you? Whether that person says, what'd you say? Or, oh, I'm doing fine, right? It doesn't really matter. The conversation has moved on. What TCP does is detect that packet didn't make it there and retransmit it at a later interval. Now, That's not, I mean, again, go back to the conversation. Think about that. It'd be like, hi, are you? How? Would just kind of at random pop into it. There's no point. Real time. The moment has passed. You know, if you're watching a movie, you know, those pixels have moved on. You don't want it to shoot in there at a later time. So unreliability can be a good thing, but most applications, I'll say the applications that most people think about when they think about using a computer, web browsing, I use the cash register application where we paid $5 for one of those little fidget spinners, and it was communicating over the server. That's where we want that reliability. And I'm just going to put reliable. I'm not going to put slow on there. It's just not as fast as unreliability because it has to keep track of things. It actually uses these things called sequence numbers. Think of it like this, you know, packet 1, packet 2, packet 3. The other side is sending acknowledgments back saying, got it, got it, got it, got it. And if the computer ever misses an acknowledgement and doesn't hear back from the other side, it goes, oh, it must not have got that. I'll go ahead and retransmit that data. And the computer on the other side reassembles and goes, there's my missing puzzle piece. Click. And now it's got all the data that it needs to reassemble that full communication. There are other protocols we can choose from at the transport layer. Or when I say we, I mean the application. But this really comprises 99.9999999% of the communication that goes across the internet and our networks today. The other thing that happens at the transport layer, I'm just going to clear all this off, is that the applications are separated from each other using something known as port numbers. In our example, that computer is running a cash register software that allows us to purchase things for $5. I don't know why $5 keeps coming back up to it. But it's communicating that over here to the server, which is probably running a database that keeps track of all the stuff that's being bought and produces reports and everything else. But what else could that server be doing? I mean, we don't know, but I mean, it could also be running an email server. It could be running a web server. It could be running an FTP, a file transfer protocol, where it's storing files. It could be a World of Warcraft online gaming server. For all we know, we don't know. It could be running hundreds or thousands of different services from that one box. So now the question becomes, we're running our little cash register software that registers this $5 purchase with this and sends it across the network to be received by this server. It's saying, hey, I spent $5 for a fidget. How do you spell it? Fidget for the fidget. You know, here's the two items I want to send to the other side. It's being received. How do I know that it doesn't accidentally receive that into the email service and send that to, you know, some unknown recipient, or you know, put that $5 purchase on the website accidentally? Well, that's because the server service that's running the cash register software runs on a specific port number. So in TCP, there are 65,536 ports. You don't need to know that, but that's a lot. Ports per IP address that you could assign. So that one server that we were just talking about could technically run 65,000 some different services. That's crazy. It would never do that. But the point is it could. And we use those port numbers to distinguish it. Here's what I mean. When that cash register sends its communication, let's just say the $5 purchase is its data. And by the way, I'm going to start doing this as we go. It's going to send it to the destination server on a specific destination port. Let's just say it's 5,000. When that server receives that $5 purchase, it's going to look at the destination port and look at the applications that are running. It will realize the cash register server software is using port 5000. Why? Because that's how the application developer wrote it. That's the bridge between the transport layer and the application layers. Is that port number says, oh, I'm handing it up here to the session layer and the presentation layer so I can understand it and store it in the application right here at the top of that OSI stack. Last thing I'll mention, the transport layer goes two ways. Your computer is probably running more than one network-aware application at a time. All right, confession time. Right now, you're looking at me, you're listening to me, but what else are you doing? What are you doing in the background? What do you have running? Do you have a Bitcoin tracker? Do you have your email open? Do you have streaming audio? Yeah, what's your distractions right now? Are you one of those people that you open your Google Chrome or Firefox or whatever browser you're using, and you've got so many tabs across the top, they're so skinny that you can't even tell what they are anymore? You're multitasking. And your computer has to be able to handle that. It's getting all of this stream of data coming into your computer, and it's having to say, here's the application, here's the tab in the Firefox browser that's receiving that. Tab 1, tab 2, tab 3, et cetera, et cetera, et cetera. So it puts it all in the same place. So when it's assembling this packet, it also includes the source port as well. So when that cache register communicates to the server and says, hey, I'm going to the destination port of TCP, it's reliable, so make sure you acknowledge this on the way back, port 5000, on the way back, it also says use port, we'll say TCP 11,511, right? I can't come up with numbers like that on the fly. So when this computer communicates back, or the server communicates back to the computer knows exactly where to put that data, which application to deliver it to. That's all the functions of the transport layer. I hope this has been informative for you, and I'd like to thank you for viewing.